Okay, Tim, let's get started. Well, I should probably move this closer. Sorry about that. I didn't. So for the people on Zoom, the previous booking went slightly over time, hence why we started a little late. But today, welcome to today's session for Stats Crash course, where we're talking about correlation and regression. And I have very cheekily called it also known as machine learning, because people who claim they do machine learning it's often just regression. Often it's claimed that the most simple type of machine learning is just simply simple linear regression. Obviously, it's not that simple. Machine learning is a whole other thing, but nonetheless, this should give us a good understanding, a good start to what regression is. Cool. Right. So let's get started. So learning objectives. Interesting. Okay. Right. Number one, we'll be talking about correlation and regression. So what are the differences between the two? I've included a handy little table, and also understanding how to perform a Pearson's correlation. Okay, that should have been corrected, but that should read Pearson's or Spearman's correlation. But anyway, but we're going to cover that shortly anyway. Spearman, so like, the javelin thrower. And then also understanding how to perform simple linear regression. Okay, so when to use correlation and when to use regression. So as you may have heard the old adage, correlation's not causation. But what is correlation? So first of all, does correlation quantify the direction of the relationship? Yes, correlation absolutely does. Does correlation show cause and effect? Traditionally, we don't. However, it's becoming increasingly common in journal articles to be like, oh, look, we saw a significant correlation, therefore it must be. And that's, to some extent, that's true and only if it depends on the experimental design. If you're able to show one variable happened before the other, you can kind of say, oh, well, it kind of causes it because it preceded it. But that goes into a lot of other areas which we won't talk about. But traditionally speaking, no, correlation does not show cause and effect. Is it able to quantify the strength of relationship? Absolutely. Both correlation and regression can do that. Are we able to predict hypothetical values? So for example, if I had a y equals mx plus c, if I had height against weight, usually height and weight are correlated. The taller you are, the more your weigh, likely. With correlation, can you use like, okay, then how about a 70 kilogram male? How tall will this person be? You're probably not going to be able to quantify how tall the person would be with correlation, but regression, you absolutely can. X and Y are interchangeable. So for correlation, yes. If I swap the X and Y axis to be Y and X axis or the other way around, whatever, you'll get the exact same values for correlation. But for regression, it's not that simple. And no, you won't get the exact same numbers. Although, of course, they will be interlinked. You'll need to do some fancy mathematics. When I say it's not that fancy, but you just need to do some algebra to get the values around. But generally speaking, no, X and Y are not interchangeable for regression, but they are for correlation. And are you able to get a p-value? That's a bit tongue-in-cheek because it seems like in science we only care about the p-values, but yes, you can absolutely get a p-value from both correlation and causation. So first of all, how do you do a Pearson's or a Spearman's correlation? So first of all, what is the two? What is the difference? So Pearson, he's the son of a farmer. No, he's not. Pearson's R, or correlation, is, so you have two continuous variables. Typically, the continuous variables are normally distributed. They have a linear relationship, and they're typically homoscedastic, i.e. they have the same variance throughout the different values of X, or different variables for values of Y. Spearman's, the javelin thrower, again, you expect two continuous or ordinal variables. However, you do not assume normality, you do not assume linearity, and you do not assume homoscedasticity. So you don't assume equal variance. Note that in correlation, there are no dependent or independent variables. There are just two variables. The null hypothesis is that the two variables are not correlated, and the alternative hypothesis is that the two variables are correlated. So As an example, let's talk about Pearson's first. Pearson's, or linear correlation. So for example, let's have height against weight, the most typical one. You expect a linear correlation, and typically the R value will be between 0 and 1. So the R value can be between 0 and 1. And then another example is maybe, let's say, IQ against the quality of lawyer. And typically that's probably got no correlation. So R is equal to 0. That's just me being cheeky. And then last but not least, maybe on the y-axis, you might have research outputs. And then on the x-axis, you might have years after getting tenure. And then you might have like a negative correlation there. And the R value will be between -1 and 0. So my point is correlation can be from -1 to 1. A -1 to 0 means it's a negative correlation. So the further along number of years after getting tenure, your research output declines. If you have no correlation, then R is equal to 0 or roughly close to 0. And then R can be close to 1. And yeah, that would be a linear positive correlation. So positive correlation, 0 correlation, or negative correlation. Just getting used to these terminologies. And then the other type of correlation that I referred to was Spearman's correlation. Spearman's, and this is typically non-linear correlation. So typically on the X and Y axis, rather than having continuous variables, you typically just rank them first, and then it doesn't actually matter what the shape is. You can have like, what is this called? A parabola maybe? I don't know. But instead you just use the ranks to get the correlations. And so I won't draw in the dots, but basically it doesn't matter what the shape is, but use the ranks to, oh, you can't even see that. So yeah, I guess what I'm trying to illustrate is that Pearson's is a linear, it assumes a linear dependency or linear relationship, or I shouldn't say relationship, but a linear correlation. And you have positive, 0 correlation, and negative correlation, whereas Spearman's is non-linear, because the reason why it's non-linear is because you use the ranks of the values rather than necessarily the actual absolute numbers. So yeah, that is correlation. And shortly I will explain how you would do it in R as outputs and how you would report the data in R. That's just the next page, and it's pretty straightforward. So thankfully in R, it's actually really straightforward, because all you simply need to do is cor.test, core.test, and just ignore what the X and Y is, but you can just go method equals Pearson. So method equals Pearson, and then you can see you get a T value, a degrees of freedom value, and a P value. And then you should also get an R value somewhere. Correlation, that's the R value, 0.998. Similarly, you can do a Spearman's correlation. So this value probably wasn't 1, it was probably 0.999999999999999, in which case it was so close to 1 that R rounded up to 1. You can see the P value is very small. So in order to report this in your journal articles, you might say method, in the methods, you might say a Pearson or a Spearman's correlation analysis was conducted between height and weight in R version whatever software, and your results might be height appears to be highly correlated, R and in brackets degrees of freedom equals whatever, and then P equals whatever. Just going to quickly take a brief gander into something else. Okay, I might just include something down here. You might have also talked about something called R-squared values. R-squared values. So an R-squared value is literally just the R. You square the R value. I will say though, if you have an R squared equals 0.8, this means that the relationship between X and Y, or independent variable 1 and independent variable 2, explains 80% of the variance. So notice how I said R squared, it talks about variance once you've squared it, and that's in line with the fact that you've squared it and it becomes variance. Also note that R squared values, R squared values can only take a value between 0 and 1. And why is that not surprising? Well, obviously it's not, because any negative value squared becomes a positive number. So even if you had like a negative 0.5 correlation, you square that and that will become positive 0.25. So as a result, there's an unspoken rule that if you have an R squared of 0.8 and above, i.e. the relationship between X and Y is explained by 80% of the variance is explained by the relationship between X and Y, then you've got a good correlation. But note that's actually, I think that's a R value of 0.6. No, I'm getting confused. Anyway, but yeah, but typically R squared of 0.8, that means the relationship between X and Y is explained by 80% of the variance. So that's the main thing. Okay. But that's correlation. It's actually really simple to do in R. So yeah. Now let's talk about simple linear regression. Often people talk about simple linear regression, and I've always struggled because it's just like, well, when are you ever going to use simple linear regression? And then actually, during my PhD, I actually needed to use simple linear regression, although in different flavors, and of which you'll experience today, because this is my data that didn't go well, but anyway. So input. So as I alluded to before, you have an input, you have independent variable and dependent variable, and they must both be continuous. So in this example that I'm going to give for this particular experiment, I'm going to use LCMS against concentration. So what I did personally, I needed to use, the ligands LCMS. I needed to use the ligands LCMS, and then I also prepared some samples, prepared known concentrations to do a calibration curve. So I prepared known samples across a certain X range, and then I had the instrument actually measure the signal or the intensity or whatever. Well, actually, in my case, I actually did like the relationship to the internal standard. But to each their own, everyone will do something different. But anyway, I had the LCMS measured version and then also the prepared sample, the known concentrations. And then what I did was I did a simple linear regression where I put the LCMS on the Y plotted against X, and data equals DF1, that's just standard. And then I came up, this was the R outputs. Now, I just want to highlight, if you wanted to read off R output from this, because basically I'll be looking at these values. So essentially I will be writing Y equals mx plus c. M is 1.04805 plus c, but it's a negative number, so it's negative 0.44046. So that's how you read off R, like the estimates are the values that you actually want. And I think I also alluded to this earlier in the course, but I'll just say that the PRT, that the probability is greater than absolute T, that's just the p-value, and the p-value's null hypothesis is whether this value, whether the estimate is statistically significantly different from 0. So you can see the intercept is not statistically significantly different from 0. Frankly, I don't care. A lot of the time you don't actually care about that p-value, but R just does it for you just in case you do care. However, I will say this p-value 2.43 e to the negative 11 means, is this value 1.048, is that statistically significantly different from 0? My question is this: if you have a gradient of, oh, sorry, I should have included an x here. If you have a gradient of 0x, does that mean, what does that mean? That means there's no relationship between y and x, because it doesn't matter. If you have a horizontal line, i.e. if you have a gradient of 0, if you have a horizontal line, it means that no matter what value on the x-axis you have, the y value will not change. And that means you have no relationship between the two variables. As a result, this p-value is often sometimes thought as important, because then this is basically, you can sometimes infer that this might be saying, is this relationship statistically significant? And then you can say, yes, the gradient is statistically significant, therefore there is a relationship. That's what some people might use to justify this. Cool, does that make sense? Nod your head, shake your head. Great, cool, thumbs up. Okay, so what did I do? Okay, and then you can also do ANOVAs just for fun, because why not? ANOVAs are great. And yeah, again, you can do ANOVA, open brackets M1, model 1, which I called it. But anyway, that's just that. Now, reporting. What can you do? How do you report this? So methods, a simple linear regression analysis was conducted on the calibration curve using ordinary least squares in R version 4.1.0. And then the results, the simple linear regression was calculated to predict LCMS values based on the known concentrations. A significant regression equation was found, F, and then 1,8 equals 2599. I will just say that 1,8, when I do y equals mx plus c, how many parameters am I estimating? So I will just say I had 10 values, right? I had 10 values. And so if I had 10 like LCMS versus concentration values, that means I have how many degrees of freedom? 9 degrees of freedom. And in order to fit this curve, I needed to use 1 degree of freedom to fit this curve. Because you can see the 1,8 in the ANOVA, I had 1 dedicated to that. Now that 1 degree of freedom is used to estimate that gradient. Notice how the intercept doesn't actually take up a degree of freedom, because it just doesn't. And so that's why you had 8 degrees of freedom allocated to the residuals, 1 degree of freedom allocated to the beta 1 coefficient, the 1.048 coefficient. So that's how you do F, open brackets 1,8 equals 25. That's just the F value I got from here. Then that's the P value I got from there. And then I just added a R squared value, 9.99, so 99.7%. And then, and the predicted LCMS values were predicted by known concentrations based on the equation, and I included the equation just for good practice. Now, there are considerations. There are some things you may wish to consider. Ordinary least squares is the default. I'm just going to say, I mentioned ordinary least squares over here. Now, this is the default thing that you do. And it's also known as linear least squares. And what this assumes is homoscedasticity. So that's why when I said okay, that's supposed to read homoscedasticity. You can hardly read it, but that is supposed to read homoscedasticity. Ordinary least squares just assumes, linear least squares just assumes, as you would normally, you just simply, every value, absolute value, just minus it and then subtract it from the mean or the thing, and then square it and then square root it. That's just how you assume it's done. There are other things that you can do to play around with linear regression. Number one, you can fix a zero intercept. So fix, I'm just going to draw maybe, about a third of the page I'm going to put on the left and 2/3 I'm going to save for the right. Now, you could fix a zero intercept. And so in this case, it might be that when you found that the intercept was not statistically significantly different, you might be like, no, I want the predicted value to go through 0, 0, and you can fix the zero intercept. So in this case, LCMS would just go through 0, 0. It would go through 0, 0, and that would be one less value to estimate. So that's one thing that you can do. Maybe in some of your theoretical models, you may prefer to fix a 0, 0 intercept, fix a 0 intercept. That's up to you, and that's up to your experimental design. Some people like it, some people don't. I personally don't, because I still think that there is value, because you can be like, if I had no concentration and yet my signal was negative 0.44, you might be like, that makes no sense. But I would say, as the scientist in me, I would say, no, that just means that there's a measurement error, so you have to shift everything down a little bit. That would be how I think about it. But again, that's different for every instrument that you use. Then the other thing you may consider is using weighted least squares. And what does this do? This accounts in part for heteroskedasticity. Now, what do I mean by heteroskedasticity? The fact that there are different variances at different values. Now, let me show you something that I had a problem with in my studies. On the y-axis, I had LCMS. However, in LCMS, liquid chromatography mass spectrometry, it's a very precise method. Now, it typically has, so I don't know why that's a negative sign. It shouldn't be a negative sign. 0.01, 0.1, 1, 10. This is a log scale, but just, so I needed to estimate the quantity of my drug, but at different scales. One at, I think that's a picomolar range, 10 picomolar range, 100 picomolar, 1 nanomolar, sorry. 1 picogram, 10 picograms, 100 picograms, 1 nanogram, 10 nanograms per mil. But the thing is, do you expect it to be accurate at the same level? Because, for example, if over here you have a value and it's plus or minus 0.1, if I read a value, if I gave the machine a sample and it was 1.3, oh, sorry, thank you. If I gave a value that was like 1.3 plus or minus 0.1, but then if you imagine that plus or minus 0.1, if extrapolated all the way down to here, if it was 0.003 plus or minus 0.1, that is a huge variance for something so precise. And actually, that's not true. That's not what usually happens. Typically speaking, you can expect instruments to be precise to maybe 1/10 or even 100th of the value. So whilst at the larger numbers, you might expect accuracies of maybe 10% or even or 1%. So meaning a value reading like 1.0 might have an accuracy of 0.1 or even 0.01. You can see how at the different scales, it might have different accuracies. So when you create your standard curve, you can see how actually, now this isn't drawn to scale, but you can see how the error bar down here will be very tiny, whereas the error bar here will be much bigger in relationship to the value. So as a result, what a common practice or common thing to do is people using weighted least squares, meaning that you account, so I think this value will account for 1 over x. So what's 1 over 0.001? I think that's 1,000 or 100. 1 over 1,000. So that's 1,000. So meaning that the variance here will account for 1,000 times as much. This one will account as 100 times as much. This one will account for 10 times as much. This will account for 1 times as much. This will account for 0.1 times as much. So you're weighting the variation or the variance in the y-axis different amounts at different x-axis values. And that's a very common thing to do when you're doing calibration curves, I believe, especially when you're crossing so many logarithmic domains. I think I needed to quantify my values only across 2. So I think I needed to quantify between, I think, 50 picograms to about 25 nanograms per mil. So it wasn't too bad, but if you guys are more into this pharmaceutical industry, as I know some of you are, yeah, well, you'll have to deal with that in much more detail than myself. But yeah, that's one thing that you may do. Oh, sorry. And the other things that other people may do, instead of doing 1 over x, they may do 1 over square root of x or 1 over x squared, and it's just a different model. So these are different ways to do it. Okay. Next is polynomial regression. So again, similarly, you expect there to be a dependent variable and an independent variable. Now the example I'm going to use here is PEF, peak expiratory flow. So if any of you have any loved ones, or even yourself, if you've got asthma, you may have once gone into the pharmacy, they would have given you something to blow into, and you have to breathe out as fast as you can to see what your lung function test, and they may have peak expiratory flow. I don't know why I wrote function, but it's often lung function, peak expiratory flow. And yeah, now typically speaking, if you have values that now on the y-axis is PEF, on the x-axis is age. So that might be the data point. I might have gotten, I don't know, what that's what, 7 people in, and someone was 10 years old, someone was 20, 30, 40, 50, 60, 70 years old, and then I plotted this on a graph. If you did a simple linear regression, as we've just talked about, you might get something that looks like this, and your prediction will be that might look something like that. Now that's a linear graph. Now there's PEF, age, PEF, age. I'm just going to draw the same 7 values, or whatever, however many values there are, multiple times. So with a, so that was a linear graph. So that's, I think, well, we just call it linear. And then if you wanted to create a quadratic curve, you would need to do this, and then this one would need to do this. God, my handwriting is getting worse and worse. I'll go to, okay, so so that's a quadratic, or yeah, we call it quadratic because it's to the power of 2. So now notice how you need to estimate 3 betas. In linear, you need to estimate 2 betas, although this one's just the intercept, so it doesn't really count. But you have to estimate these 3, or if you have a cubic, if it's a cubic relationship, you have to estimate even more coefficients. Now, a quadratic coefficient might look something that looks like this, whereas a cubic one typically has multiple points of inflection. The fact that it switches direction twice, that's just the property of cubic curves. Now that's unlikely to be true, but for various reasons. Notice how, no, I'll finish that thought later. But yeah, so you can do polynomial regression by simply having, doing this, beta 0 plus beta 1x, beta 0 plus beta 1x plus beta 2x squared, beta 0 plus beta 1x plus beta 2x squared plus beta 3x squared. This is what statisticians like to use. This is the nomenclature. This is the traditional sort of way they write things. Yeah, beta 0, beta 1x. Now the betas are all just coefficients or estimates. So on the previous page, it would have just estimates. Those are the same values. Let me just zoom out again. There we go. No, lost it. Okay, there we go. And so yeah, they're just numbers, and the x is just the one on the x value. Now, what are the pros and cons? Pros, well, it's a very easy thing to do. It's very easy to run this type of analysis, and it's very well understood. People know what polynomial regression is, and it's a very simple thing. But I would say the cons of this is that it's actually really hard to make sense of what these 3 coefficients actually mean. Like, so what that you've fitted a quadratic equation, but what do the coefficients actually mean? And I'll finish that thought in the next section. But one thing I did want to, so here's an output. So the formula was PEF, peak excretory flow, was against polynomial A, 2. This meant I wanted to fit a quadratic one, quadratic meaning x to the power of 2, and data equals lungs. And then you can see how the x to the power, what's x to the power of 1? It's just x. And so therefore the estimate, the beta 1 was negative 111.5, whereas beta 2 was negative 282.923. And again, similar things, as I said, it's statistically significantly different from 0. Whether you care about that or not is up to you. Typically you should, but yeah. And then you also get R-squared values. Yeah, and that's how you would report it. So a polynomial regression was calculated to predict the LCMS values based on the known concentrate. Okay, that's not right. It should be about lung function. But anyway, a significant regression equation was found, F2,4. Now, this is what I wanted to finish my thought on previously. Notice how in the cubic relationship, you need to estimate even more parameters. And the more parameters you need to estimate, if you did, I don't know, what do we call an OC? Okay, if you did x to the power of 8, that means you needed to estimate 8 parameters plus the intercept. But that means you need to use 8 degrees of freedom because you have 8 parameters. And because if you only have 7 values, how many degrees of freedom do you have? You only have 6 degrees of freedom. So actually, it's actually dependent on how many values you have. So with n equals 7, okay, we have 7 values here. That means the maximum you could do is like 6, is to the power of 6, which is a 6. Okay, I can't remember what they're called. But you can only do a polynomial regression up to the value of beta 6. That's probably still not good practice because that means you've left no degrees of freedom for the residual and actually you'll overfit your data. So in which case you should probably do a x to the power of 5, but even then that's probably not good. Typically speaking, an x to the power of 2 or 3 is probably good enough. But yeah, you don't want to estimate, you don't want to make it like too top heavy on these. F2,4. So because this is a quadratic equation estimation, this is only to the power of 2. We used 2 degrees of freedom to estimate 2 values, and that's it. Yeah. Okay, I think I waffled a bit too much for that, so let's keep on going. So remember how I said it's very difficult. It's hard to understand it's hard to understand what these beta values mean once you get to when the dimensionality gets too high. Well, that's why you might want to use nonlinear regression. Now, the example I'm going to use here is Michaelis-Menten kinetics. That's a very famous enzyme kinetic equation, Michaelis-Menten kinetics. And so the reason why you might want to use nonlinear regression is because if you know what the equation should be, or you have a theoretical understanding of what the equation should be, then it would be a good idea to use nonlinear regression. Now, for example, the Michaelis-Menten, the most basic one, would be using something like Vmax times concentration divided by Km plus concentration. And I'll just explain what each of these mean. Not that you do need to know it, but I'm going to explain it because it's a very common thing to do. So yeah, this Vmax is a constant. Km is also a constant. So the Michaelis-Menten equations, all they're trying to do is they're trying to predict concentration of, I think, concentration of substrate and the rate of reaction. And so by plotting rate of reaction against the concentration of substrate, you'd expect that this is basic enzyme kinetics. As you have increased concentration of substrate, you have increased rate of reaction. Now, you might just have values. You might have like prepared samples. You might, let's say you have prepared five samples at different concentrations. Let's say you prepared 5 substrates at different concentrations, and then you dropped in like a known weight of powder, which was, I don't know, a catalyst or an enzyme of sorts, and then you measured the rate of reaction by, I don't know, the amount of hydrogen that was made or whatever. And you got these 5 data points. Now, if you were to fit it using linear regression and all that, you'd get different things. And similarly, if you did like a polynomial regression, you might be like, I don't know what the beta values mean. So that's why you might do nonlinear regression. You might try to fit this equation in. And indeed, this will fit the equation very well because we do know what a lot of these things mean. So first of all, what does Vmax mean? Vmax is the hypothetical velocity, the maximum velocity of the equation, the maximum rate of reaction or the velocity of reaction. So it's the fastest the reaction can occur. And if you just imagine, the Vmax is a hypothetical limit because it's like, oh, I can't remember the name. Anyway, it's a value that asymptote, that's the word. It's an asymptote that you cannot hypothetically reach, but it tends towards, the value tends towards. Now, if you imagine there's a value where Vmax is divided by 2, the half speed, Vmax divided by 2, and the concentration at which that occurs is Km. So these are the values that you may have, Vmax and Km, and it's just if you know that this reaction that or experiment that you're doing follows Michaelis-Menten kinetics, like this equation, you might wish to instead run nonlinear regression to start off to model this, and that way you actually get an estimate for Vmax and an estimate for Km. And if you got an estimate for Vmax being 1.375 and an estimate for Km being 0.628, you can actually just say, oh, well, I know what the Km of this enzyme is. I've now discovered something new and I'm going to publish in Nature. So that's like the benefit of trying to fit things to known equations. And that's what nonlinear regression is used for. Okay, right, so let's go through the output. So the output to this would be rate is against concentration times Vmax, as I said, concentration times Vmax, divided by, in brackets, Km plus concentration, and then we use nonlinear regression, 1.375, 0.628, and then, yeah, it's a very simple equation in R, which in the exercises we'll do, it's literally one line. The more complex your equation, the longer it'll take. Provided it's not too complex, like running this, if you had 5 data points trying to run this, it probably would take you like half a second to run, if that. That said, I will also add that when you run nonlinear regression models, you need to input like a reasonable value to start off. Like R itself won't really know where to start off. Like what value should Km begin at? Should it start at 0.0001? Should it start at 0.1? Should it start at 1? Should it start at 1 billion? Like it doesn't know where to start, so you actually need to feed it. Just start around 1, and then it'll start fitting it to whatever it was. But then remember, some Kms are like to the power of -12 or whatever. So you need to give it a starting value, and that's when it would be useful to refer to previous literature and say, oh yeah, Smith et al. Said it was 0.1, so that's what I'm going to start with. So yeah, in your report, you would write methods. A nonlinear regression analysis was conducted using NLS function in R with the equation concentration equals rate times Vmax divided by Km plus rate. And the results, the nonlinear regression estimated the parameter values to be Vmax equals 1.375 and Km equals 0.628. So yeah, pretty straightforward stuff. And that's nonlinear regression. Now, that said, you can be like, this value, now I'm just gonna talk around the subject. Now you can see this is for n equals 1. This is all taken presumably from the same subject. Let's say this was enzyme kinetics for 1 rat. And then if you had 10 rats, then you might notice that, oh wait, that's 10 different models you need to estimate. But then how do you get the population average? How do you get the population average Km? Do you just mean all the 10 values? Yeah, you could. That's actually what's done. And you average all the 10 Vmaxes. But then what if now I said, okay, now I've got the 11th rat here, and this 11th rat, I have these values. Now tell me, if I was to give this rat this concentration, what would its rate of reaction be? Like, then how do you extrapolate from the population data back to individual data? And that becomes an incredibly complex conversation, and that goes into the fields of pharmacokinetics and pharmacodynamics, pharmacometrics, which has taken me too long in my PhD to try to figure out, so I've given up on that. So yeah, no, I mean, we have professors in pharmacometrics, so it's a very detailed thing. Anyway, so yeah, so it's an active field of research area, and yeah. Okay, let's talk about the next thing I wanted to talk about was logistic regression. So logistic regression is really cool. The input is a dependent variable. So your dependent variable up until this point, for most of this course, it's always been a continuous variable like height. Now, or a concentration of whatever, or outcome, or whatever. However, now we're now changing the dependent variable to be a discrete variable with only two possibilities. So the dependent variable is now, for example, stroke versus no stroke. And the independent variable could either be continuous or discrete. So now we're now predicting not a continuous variable, but now whether something happens or not. And that's kind of cool. And it's based on something called, well, it's based on log odds. So this is why I wrote but the dependent variable has been transformed into log odds. I'm going to write in brackets log odds. And that's log, the probability of it occurring, divided by the probability of it not occurring. So odds, the p divided by 1 minus p is odds. So, and odds, what does odds mean? It's not actually a very intuitive thing, but it's the probability of an event happening divided by the probability of the event not happening. So if you had a fair coin, tossing it, and I asked you, what are the odds of landing on heads, what would the odds be? Just be 1, right? It'd literally be 0.5 divided by 1 minus 0.5, which is 0.5. So 0.5 divided by 0.5 is 1. So what if I said, let's just say you entered into a race which you had 0.8 probability of winning. What are the odds of you winning if the probability of you winning was 0.8? The odds would therefore be 4, because it'd be 0.8 divided by 1 minus 0.8. 1 minus 0.8 is 0.2, so 0.8 divided by 0.2 is 4. It just means it's a little bit not intuitive. It's a little bit different from risk, but nonetheless, that's what it is. I think it's really cool, so I'm going to delve into a little bit more deeply. Not that you need to know it, but I think it's just useful to gain an appreciation of how it sort of works. So an example we're going to talk about is the probability of a stroke occurring. And then let's say we ran a clinical trial where we either gave people the drug X or a placebo, but we also knew that, people who are older are more likely to suffer a stroke. So we wanted to account for age. So we have these two independent variables, and then on the dependent variable, we have the probability of stroke. So we simply did a formula, and it's a generalized linear model now. And then we did formula equals stroke is dependent on treatment, which is drug X or placebo, plus age, and the family is binomial. Family just means the family of distributions, and right now we're talking about the binomial distribution. And the data is just the data frame, which I called it logit_df. Now I wanted to, so this was the output, and I wanted to sort of use this to sort of explain a few things. So first of all, based on this output, what is the probability of a 65-year-old who received drug X and suffering a stroke? What is the probability of a 65-year-old who received drug X? Okay, that doesn't make grammatical sense, but what is the probability of a 65-year-old who received drug X to suffer a stroke or whatever? Well, we would probably do log, so log P, 1 minus P equals negative 12.3, and I'll explain where I get these numbers from. 0. And then 0.1926, open brackets, 65 minus 2.4254. So where did I get negative 12.3 from? I got it from the intercept. It's just the estimate over here. What's an angle? Sorry, team. So again, it's based on like the y equals mx plus c model or whatever. So the negative 12 comes from the intercept. Then where does the 0.1926 come from? Well, it just comes from here, the estimate of the age. That's the gradient. And then you multiply it by 65, because I said a 65-year-old. And then you minus 2.42564. Why do I minus this? Because they received drug X, and notice it's treat 1. And because I know when I wrote the data, I meant that when its treatment is 1, it meant they received drug X. And if treatment was 0, that means they didn't receive drug X, i.e. they received placebo. So simply, that's the equation. So you can, if you got a calculator out and did this, I've done it for you. So you would get something that looks like this. Equals negative 2.21824. So if you wrote all of these numbers out and calculated it out, you'd get this value. And by the way, this log is actually like natural log. So in order to get rid of the log symbol, all you need to do is e to the power of on both sides. So e to the power of negative 2.21824. That's how you get rid of log. That's log rules that you may or may not be aware of. It's been a while for most of us, I understand, but that's the thing. And then now all you need to do is solve for P. So solve for P probability, which is, the probability that I want, that I've asked you to solve for. Sorry, I don't know why I did that. And then if we did this, P over 1 minus P equals 0.1088 ... and I'll save you the trouble. The probability is 0.0981. So in here, in this, I have been given the information. They're a 65-year-old and they received drug X. What's the probability? And you can absolutely solve for that, right? You've input the age and what drug they received, and then you now output the probability of suffering a stroke. And that's a pretty low probability. They've got a 9.8% chance of suffering a stroke. Okay. Now let's do what is the probability of a 65-year-old who received placebo instead and suffering a stroke? Again, that doesn't make much grammatical sense, but all right, let's do that again. So log P over 1 minus P equals negative 12.3116 plus 0.1926 times by 65. And then we minus 0. Obviously, you don't need to write minus 0, but why do I say minus 0? Because they don't receive drug X, so they don't receive this, they don't receive that coefficient. So it's just minus 0. In fact, you could probably just omit that and not write minus 0. But that would be what the value is. Then similarly, you calculate it out, equals e to the power of 0.2074. P over 1 minus P equals 1.23. Solve for P, and that's just a bit of arithmetic. And then P equals 0.55166649, etc., or whatever. I promise there's a point to this. So now question 3 asks, calculate the odds of question 1 happening in terms, calculate the odds ratio. So first of all, we've already calculated the probability And then, right, in order to calculate the odds of question 1, so the probability of it happening versus not happening, so it would be 0.0981 divided by 1 minus 0.0981. So okay, first of all, let's do question 1 odds, Q1 odds equals 0.0981 dot 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 divided by 1 minus 0.0981 dot dot dot. And then question 2 odds equals 0.55166 dot 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 divided by 1 minus 0.55166 dot dot dot. And then the odds ratio, and I'm not going to actually calculate that out for you because I don't really care. But what I am going to do is I'm going to calculate the odds ratio of comparing a 65-year-old who received placebo suffering a stroke compared to a 65-year-old who received drug X suffering a stroke. So I'm going to do the question 1 odds ratio divided by the question 2 odds ratio. The question 1 odds divided by the question 2 odds. And I'm going to tell you that I did that. So Q1 odds is that value, and then I put it into here. Q2 odds is this value, and then I put it into here. And I'll tell you that the value is 0.088. What does that mean? So I'm just going to write out in English what that means. So this means person who received drug X is 0.088 times as likely to have a stroke compared to person who received placebo, compared to person who received placebo. Okay, that was a lot of arithmetic. Goodness, and you can hardly even read that. Oh, it's like life without glasses. There we go. Now, why is 0.088 of any interest to you? Yeah, I've forgotten. No, I've not forgotten. It's actually written over here. Oh, sorry. That's just what I wanted to write. And I'm assuming that we've all done that. It's just written up here, actually, 0.088. That's the odds ratio. And that's supposed to show that actually the odds ratio is sort of inbuilt into this whole thing. In that, so first of all, is drug X protective or is placebo protective? Yeah, drug X. So treatment 1, for those people receiving treatment 1, which is drug X, they'll have negative 2.42, which is the log odds in the log domain. Negative likely, they'll be less likely to. So, and then when you do the odds ratio, it actually does it for you. So, okay, so one of the nice things about the R output is it inputs this table of the odds ratio. And then with age, is it increasing age or decreasing age, which is associated with stroke outcome? It's increasing age, and because the odds ratio is more than 1. So an odds ratio of greater than 1 means you're more likely to suffer that. So treatment 1, because that's less than 1, it means you're less likely to suffer a stroke. That's the sort of the odds ratio. It's all basically like, if it's above 1, more likelihood, less than 1, less likelihood. And and one of the R outputs is calculating these R odds ratios, and that's why it's quite nice in that yeah, it is a generalized linear model, but it's just converted everything into the log domain, and that's why it's so powerful. This odds ratio thing, 0.088, is referring to this, and like it doesn't actually matter. If I changed all of these numbers to like 50-year-old versus 50-year-old, you still would have come out with 0.088 because literally you've kept everything else in the model the same. You've kept the age the same in both. However, you've just changed one aspect, which is just drug X versus placebo. And yeah, that's the point, right? So yeah, that is what I was trying to say. So you can see how, what if you had like a 50, so now you can do like a 65-year-old who received drug X versus a 50-year-old who received placebo. That's two things that are changing at one time, and you can use this model to estimate the personalized likelihood of receiving a stroke. And that's the nice thing about logistic regression, is that you can do this. Note that this means that this is all additive, and obviously there's problems with interaction effects, so that's what makes it less, a little bit more complex. But yeah, that's one strength of logistic regression. Okay, so that's how you'd report it. Two predictor logistic regression analysis was conducted in R. Two predictor meaning the treatment and the age, and then also results. The logistic regression analysis showed significant effects in drug X in lowering the odds of stroke compared to placebo. Odds ratio is 0.088. Typically, you would be expected to include the 95% confidence interval. Oh wait, you can't even see what I'm pointing at. Right, 95% confidence interval, and where does that come from? From here. And if you're confused as to why it says 2.5 to 97.5, that's just a fact. We want the middle 95% of the spectrum. So 2.5 to 97.5 is the middle 95% of, yeah. So yeah, and then you can include the p-value 0.0274. Where does that come from? It comes from up here, the treatment effect. So that's receiving drug X. So you'd be like, oh, the pharmaceutical companies would be like, yeah, look, our drug X does stuff. Now give us millions of dollars. And then significant effects of increasing age on susceptibility of stroke, and that's also significant. And I think that's it. All right, yeah. Last year I wanted to include hazards ratio, and so we could play around with Kaplan-Meier curves and survival analysis, but I ran out of time to include that, so maybe another year. Okay, now let's move on straight on to all of this stuff and get this show on the ground. What? I don't know. Okay, just gonna change up this, stop share. What do I need to do here? I need to share screen from here. Okay. I need to hide video panel, and I need to hide floating media controls. So we have course code, and then we also have, what's today's seminar? I don't know why there's a 5B in there, but let's just go with it. What am I doing? I need to change this to lectern computer. And then you can see this. Great. Awesome. Okay. So as per usual, I recommend you set your working directory. You don't actually have to work with the working directory, but it's just easier when you have to save or load stuff. So first of all, I hope you all know how to set your working directory. If you don't, feel free to come on up. Happy to show you on your computer. Yeah, the fastest way I do it is just Control-C, my working directory, and then set working directory, do that. But R prefers forward slashes. Yeah. Then you set your working directory and it's done. Oh, you should run library commands always to begin with, so you don't have to run it midway. The calibration curve data I just included in here. That was the calibration curve, so you can see the else. I tried to do 0.001 concentration. These are all my standard known concentrations, and the LCMS gave me these values. Yeah, I didn't do too good of a job, but I think it was a decent job for my first try. And so you can see my first data frame was that. Then you can run a Pearson's correlation. So I think it says perform Pearson's correlation analysis. And so that's how you do it. You just run the Pearson's correlation, and then the R is that. And then you can run Spearman's correlation, and yep, that's perfect. It's very highly significant and very close to 1. Now you want to do simple linear regression, but with ordinary least squares, and that's how you do it. That's the code. And so now I fit it using the LM command, and then a summary to view it, and then you can see that's where we got it in the lecture. And then you can also do an ANOVA if you wanted to, just for fun. Now I think I asked you to do simple linear regression, but fix the 0 intercept, and that's the notation you want to do. LCMS is dependent on 0 plus concentration, and that's how you do it. And then summary, and yeah, so you know there's no more estimate, and yeah, and then ANOVA, done. So you can see in the summary one, there is no coefficient for the y-intercept, the intercept. So if you compare it with summary M1, you can see how there's an intercept, but summary M2, there is no longer an intercept because we fixed that at 0, and there's no error associated with that because you fixed it at 0. Now I think I told you next to do simple linear regression with weighted least squares. So notice how the conc, C-O-N-C, is the x variable. So that's why I included an argument weights equals 1 over conc, 1 over x. So yeah, so you just run that. That's how you run weighted least squares with 1 over x, summary, and then that's that. And you just have different values because obviously you've done something slightly differently. And then you could also do 1 over x squared, which is a bit, I think it's less common, I'm not sure. But yeah, it's just running it again. The model's going to be slightly different because you've weighted the variability slightly differently. And so now, what I asked you to do now is I asked you to plot all 4 lines overlaid onto the data. And so this is this all over here. So first of all, you create a function. Now I really haven't touched on creating functions in R because it's a whole nother can of worms, which I didn't really want to do. But basically, what this M1 function, I've just called it function open bracket x, close x. It just means M1 function is now going to be a function which, if you give it a value x, it's going to do this following thing to it, which is just a mathematical calculation. You can always embed other things like the mean of something, or you can do all sorts of things. But anyway, I defined the functions like this. There are 4 functions to define. Where did I get these values? Well, remember how I'd think it was it summary M1? Sorry. Summary M1. M1 was 1.048 minus 0.44. That's where I got these numbers from. And then where did I get M2? Sum. So yeah, I hope you understand where I got these numbers from. Great. So I first chuck in those numbers, and then I do the GG plot, and then I think I add the points, alpha meaning transparency. I don't want it to be fully, that's why I just put 50% transparency on it. And then I add the 4 different statistical functions, and I give them different colors. The scale Y, scale X, I just change the X and Y axis. I like to use theme classic, and then these are just, you'll see what they are. They're just labels. And then if I plot this G1, you're going to see something that looks possibly a little weird. Right, like this. So you can see how I had 4 models. The first model was just a simple linear regression. The second model in red was the fixed 0 intercept. The third model in blue was, I think, 1 over x weighting, and the green model was the 1 over x squared. And so when you do 1 over x squared, you heavily weight towards the lower values. So if I just look at, was it DF1? I think it was DF1. Yeah, it was DF1. You can see how I have so many values below the value 1. So actually what I'm saying is that I want these, how many values are below, are 1 or below? 6 values are below 1, whereas above 1 you have 5, 10, 25, and 50, right? So that's why sometimes you want to do weighting. You want to take weighting a little bit more seriously. But yeah, so that's how you can plot all 4 lines, and then you can decide which line you feel is good, which line you like, which concentration, or which line you, sorry, stroke, having stuff, words. No, you can decide which model you want to use. Great, let's move on to the next one. Peak expiratory flow. You grab the first 7 people off the street, and they happen to be exactly 20, 30, 40, 50, 60, 70, and 80 years old, respectively. You measure their peak expiratory flow using a peak flow meter, measured in liters per minute. Using these 7 people and their readings, you aim to generate a graph such that you can predict a person's PEF based on their age. Basically, I just want to see what their peak expiratory flow is, and these are their 7 expiratory flows. And as I said, they happen to be exactly 20 to 80 years old. You can just plot that very easily like that. So peak expiratory flow on the y-axis, age on the x-axis. Nice and simple. And I think for questions 1 to 6, I'd ask you to perform a first order polynomial, a second order polynomial, third, fourth, fifth, sixth polynomial. How many polynomials can you plot? You can only plot 6 because there are 6 degrees of freedom. So yeah, that's what the next several lines do. And I'm just going to go through them because it's not very difficult. You can see the only difference, like how do you do it? PEF is dependent on poly, age, comma 1, raw equals raw, meaning raw values, and you just keep running them. And then you can see which one's the best model by looking at all the summaries of poly 1 model, poly 2, poly 3, poly 4, poly 5, poly 6. I just want to draw attention to poly 6. With 7 people, how many degrees of freedom do you have? 6. And in order to do a to the power of 6 model, how many parameters will you have to estimate? 6 plus the intercept. And so if you need to estimate all 6, that means on the numerator, you've allocated 6 degrees of freedom to the numerator. But then how many degrees of freedom have you allocated to the denominator? 0. So you can't divide by 0. And that's why you can see on the screen, all of these are NaNs, not NaN stands for not a number, meaning, this is crazy. Yeah, so that's why it wouldn't have given you anything. So yeah, fun times. Anyway, now what do you do? I think I say using ANOVA, determine which model fits the data best. Oh, right, I forgot you could even do that. No, I'm joking. I do know why you can do that. Okay. Wait, what was that? 5.2.7, summary poly model. Sorry. Okay, so what I think I was talking about was you can do poly model. I think if you do this sort of thing, you can look at sort of okay. Let's write this. ANOVA poly 1 model, ANOVA poly 2 model, ANOVA poly 3 model, ANOVA poly 4 model. Oh, typo. If you just look at these different models that I've labeled them, just pay attention to this number, 7,503.6 divided by 5 equals 1,500.7. The next one has mean square 156.8. The next one has 96.6. Next one has 66.9. And then the next one has 91. Do you see how it keeps on decreasing? 1,500 goes down to 156, goes down to 96, goes down to 66.9, then goes back up to 91. And that's just because of the relationship between sum of squares and degrees of freedom. As you decrease the degrees of freedom, you decrease the residuals, and so that's what the ANOVA function can do. So when you do this sort of thing, there is such, you can use the ANOVA to determine which model is the best model. So poly model 1 had, I think, 5 degrees of freedom in its residual, which is why it was 7,503. And then everything compared to that, this one was probably the best model, and it just does some ANOVA stuff to compare it, and that's, yes, you can use ANOVA to determine which model you think is best by looking just at the residuals. But I don't want to go in too deeply about that, because more often than not, you can just look at the data and you can kind of get a good gauge of what's the best. All right, next up, I believe I'd asked you to plot the best 3 polynomials. Plot the best 3 polynomial model lines overlaid on the data. So I only just did poly 1, 2, 3, 4, and then I plotted it, G2, and then let's just G2. So the best, oh, okay. I said plot the best 3, but I plotted the best 4. Oh, well. So yeah, I plotted, there's a linear model in there. Linear model, clearly not very good. Then you've got the red line, then the blue line, then the green line, and it's sort of out of frame. But nonetheless, I think, yeah, you can choose which line you think looks best. I would guess that either the red or blue line looks best, and you can always look at the summary models to do that, to check which one's best. And yeah. And I think the last question is, suppose a 36-year-old walks into your clinic, what would be their predicted peak excretory flow? And this would now be up to you to be like, well, which model do you think is best? And so I think I thought poly 2 function was the best, poly 2 being the poly 2 model, and the poly 2 function, I input all the values into it. So simply, I just went poly 2 function, open bracket 36. So their predicted peak excretory flow is 611.5238, or 611 liters per minute. And if their value was large or small, well, yeah, it doesn't matter. That's just their expected peak excretory flow. Okay. Next question, Michaelis-Menten. You discover a new antiviral enzyme. You wish to find out the enzyme kinetic properties. You supply differing concentrations of viral fragments, 0.1, 0.5, 1, 1.5, 2 nanograms per mils, and then you measure the rate of antiviral enzyme activity using a fancy machine measured in micromoles per minute. So now you want to perform okay, I asked you to first perform polynomial regression. So first of all, nonlinear regression. So I create a data frame that looks like this, NLR, and you can see how we've got the rates and also the concentrations. Then you can, fit all the polynomials by linear model, and we've already shown this. I've already shown you how to do that. I'm just going to run through them. So now we've done all 4 polynomials. Number 5 says, perform nonlinear regression using the Michaelis-Menten equation. So this is me doing that right here. Notice how I went rate is dependent. Okay, so first of all, I'm just going to show you what NLR is. The data frame is NLR. And notice how I'm still using the same names of the columns. So that's why I use rate is dependent on concentration. I'm using the same names, so R will recognize that. And then I'll put Vmax times Vmax, and then Km plus conc. Notice how Vmax, R doesn't know what Vmax is, and R also doesn't know what Km is. So as a result, so data equals NLR, I'm saying R, go look at the object called NLR, which is a data frame. But notice how I have this argument, start equals list, Vmax equals 1, Km equals 0.5. That's what I was talking about before, how you need to tell R, Vmax, I want you to pretend Vmax is a constant which is valued 1, and just figure it out from there. So just start it at 1, and it might be around 1. And Km, it's probably going to be around 0.5. And this is when you probably need to rely on previous literature to get that value. Or you could just do it blind, just give it random values and hope that it works. So I've just run it, and you can see it took less than half a second, or less than a tenth of a second to run. And then, yeah, those are your values. Vmax is 1.375 and Km is 0.628. Very quick, very easy. Now, I think the final question says, plot the best polynomial regression line and the nonlinear regression line overlaid on the data. So let's plot it. So I think I noticed, so I thought the quadratic equation was the best. So that's why I used these numbers. So I create a function called poly2 function and function, standing for Michaelis-Menten. And then I simply did this, and yeah. So let's plot this. Let's have a look at G3. So in red, we have, I believe, the polynomial equation, the quadratic equation. You can see how x, or concentration, has x and then x squared, whereas in blue is the Michaelis-Menten equation, where we have Vmax and Km. Now, it's hard to say which one is more accurate based off this. But that said, using the nonlinear regression, if, for example, I gave a concentration of 3 nanograms per mil, do you think the blue one or the red one will be more accurate? I'll ask the question again. If I supplied a known concentration of, I think, antiviral fragments of 3 nanograms per mil, do you think the blue line or the red line will be more accurate? Probably the blue, because it's tending towards a higher value. It's tending towards the asymptote, the Vmax. And whereas the red one, it seems to go down afterwards, right? And that's the limitation of polynomial equations, in that, like, we don't actually know what these numbers mean. Whereas in the blue, in 1.375 and 0.628, we do know biologically, biophysically, what they mean in the context of enzyme kinetics. So that's the strength of nonlinear regression. Last but not least, let's move on to logistic regression. So we have 30 patients who are at high risk of stroke. You are testing to see an experimental drug X, whether it's able to reduce the incidence of stroke compared to placebo. However, because you're aware that older individuals are more likely to suffer from stroke, you also record the patient's age. So now I think they perform a two-way chi-square test on stroke occurrence versus treatment group. So let me explain. So first of all, we load in the data. We have 30 patients, and we also have their age. So with this, you have drug X and stroke. So I'm going to change them into factors. That's a common thing to do. So let's just look at structure, logit df. So now we have changed treatment and stroke into factors. We should probably change ID into a factor as well. And run that. Great. Now, of course, we could first do this. We could create a table 1 of this. So I think these are people who don't get a stroke, and these are people who do get a stroke, and these are people who receive placebo, and these are people who receive drug X. Oh, right, I do this. Okay, let's look at table 1 again. There we go. So yeah, you can see no stroke, stroke, controlled drug X. And what can you do with this? You can absolutely do a chi-squared value. You can do a chi-squared test. But remember how we said that chi-squared tests are invalid if, not every cell has a value, expected value of greater than 5. So yeah, that's going to be a problem. Run. Okay, so I've run the chi-squared test. It should be for table 1, sorry, not for table. And then we get a p-value of 0.1405. That's not significant. That means that drug X has no effect, right? Well, but remember how I said how, you needed to apply continuity correction. There was a problem because the expected value wasn't greater than 5. That's why you can do a Fisher's exact test, but that's still not statistically significant. So what are you going to do? You're going to run multiple statistical tests and p-hack your way into significance, right? No, you're going to run a more biologically valid test to better capture the true relationship of the data, right? So you're going to do a logistic regression, and that's another type of thing you can do, which we've talked about. So that's how you do it. And then you do a summary, logit. These are the values we covered in the lecture. And then summary, and then exponentiate. What is this? And then you can use that exponentiate thing, because as I said, to get rid of the log function, you can exponentiate it in order to change it into the odds domain rather than the logistic domain. So we've finished the two-way chi-squared and the Fisher's exact test. Now part 3 says perform a 2-predictor logistic regression, which we've just done. And now I ask you to plot the predicted logistic regression model line overlaid on the data. So now I ask you to plot the data. So let's do this. Okay, what's this? So first of all, yeah, I have no idea. I do know what that is. It just changes all of these into, I don't know. Anyway, so B0 is negative 12.3116. Where did I get that from? I got it from the summary value. So I'm just taking the estimates, the means or whatever. and then B1 age and B2 treatment, and then the logistic function of the control group, so the people who received the placebo, I just manually calculated out all of that value, all those values, like we did, before. And then we ran G4, graph 4, and then we plot this. And then you can see how in blue are the people who received drug. So you can see in blue are the people who received a stroke. So obviously they're either going to be 0 or 1, meaning they either received a stroke, suffered a stroke, or they didn't suffer a stroke. But then you can see these logistic functions. So for, let's say, a 60-year-old, you can see the people who are in the placebo group are much more likely to suffer a stroke than the people who receive drug X. Drug X could be a statin or whatever, right? So that's hopefully quite intuitive of how you might plot this data. And then you can save the data, and that's the line to save the data, save the plot if you want. But yeah, that's an example of a logistic function and how you might plot the data and how you might analyze the data. And and I believe that's the end of the